Hello. Hello, can you hear me?
Hey there.
Oh, yeah, okay, good. I was starting to worry. I was
Yeah, I had, sorry, I didn't realize I was both muted and had my camera off. How are you doing?
oh good, not too bad.
Are you in Syracuse?
Yeah, yeah. Do you want to see a picture of the snow?
Sure,
And
yeah.
move my camera and point out the window. See
Okay.
students and snow. So really there. Yeah.
Kevin, have you joined us as well? Interesting. Okay, well, I think people will just come trickling in. Do you want to see if you can share your screen just as we start?
That's what I was. I think this worked out.
Yeah, that looks pretty good.
Okay, good.
Are you showing any video or audio that you want to try?
Video. Actually, not very much. They're actually more like animated. Let me just pop over to something real fast, and then I'll probably get good.
I'm glad to see the Poisson Ratio is making an appearance.
Oh yeah, absolutely.
It's always 0.32, right?
Yeah, not today.
Okay. Yeah. It's sort of...
I take it.
What?
Oh, am I not sharing my screen anymore?
Yeah, your share screen went away.
Now in moving. I mean, it works for me.
Yeah. Okay. Yeah, it seems to be fine. So I'm trying to remember. We must have overlapped briefly at Santa Barbara if you graduated in 04.
I think we probably did. I mean, I remember you, I believe.
Okay.
You were, when did you graduate, I guess?
I graduated in December of 2000.
Okay. I think I still thought I was going to do something not soft back then. I don't think I even knew that I was working on it.
Okay.
It was all the way back then.
Who was your advisor there? Who?
Well, I guess.
Okay, great. So did you overlap with Andy Lau?
Only a little bit. He was there for 1 year. Did he graduate in 2000 also?
99 or 2000. He started my year, which was 94.
Yeah, so it wasn't we didn't have a big research overlap in terms of when he graduated, but we did end up collaborating afterwards.
Okay.
But somewhere here.
Good. And so I saw you moved to Syracuse right at the start of the pandemic.
Yeah. Don't ask me where any of the good restaurants are yet. I haven't been to very many, so.
Yeah. Did you bring students with you, or did you mostly start afresh?
I brought 2 students with me. I had just graduated. Actually, I guess I brought a little more, but they're mostly graduated. I have 2 left. One of them technically still a UMass student. They're graduating in, I believe, 1.5 years if all goes well. And then there's another student that did come over, and she ended up not moving here, even though she's here.
Okay.
Yeah. So everything's all wacky.
Okay. Good. Yeah. Let's see. So I think we're just sort of in a holding pattern as people join. I advertised your talk. I'm teaching first year honors first year sequence, and I advertised your talk to them. So just be aware there'll be some first years in the room, I guess, along with the usual group.
Yeah, I think I have that covered.
Okay.
I don't know how do questions usually work with.
It's really up to you. If you say that you want people to raise their hand or interrupt or just wait to the end, we can accommodate any of those.
I prefer to try to simulate as much like normally in talks I would prefer people to
so your mic is cutting in a little bit, cutting in and out a little bit.
Okay,
Yeah.
let me see what I can do. Let's try. Just give me a second to play around with some of the settings here.
Yeah.
Okay. Yeah, I just switched microphones. Does that help or hurt?
Just talk a little more.
Okay, so here I am. I'm talking. Can you hear me all right?
Yes, it's very different sound quality. It's much more hissy.
Oh. All right, there's another solution though. I can go back to the computer mic and I will move the computer closer to me.
Okay. That might work. The other one wasn't cutting in and out, but it was hissy. So
okay. So hopefully that's better.
Yeah, that seems fine. I think if you stay close, it'll help.
Yeah. All right. Yeah, that should be fine. And so I would prefer to be interrupted when people actually have questions.
Okay.
But it's harder to do, obviously, when you're virtual because of the the lag.
I can definitely so I think you should announce that at the start of your talk. Let people know.
Okay.
And I will also monitor the chat. And if it seems like there's something to interrupt you for, I'll do so.
Sure. Okay.
And so we will start, just a couple minutes after the hour, and we're really supposed to let people go at 5. So if you are wrapping up at 10 till or maybe 5 till, that's probably best.
Okay. I think I can do that.
Okay. Have you been giving any in-person talks?
Not in a long time, actually. I've given a bunch of virtual talks, and everyone has a different format, which is why I feel like asking.
Yeah.
The questions are good. Sometimes you just sit and talk for, 45 minutes because nobody says anything. Sometimes they're more lively.
Mm-hmm. Yeah, I've been watching a lot of talks asynchronously.
Really? How do you find that?
Great. Like, speed it up. Slow it down when you need to again, like 1.75 times. Everybody who's here listening, of course, you should attend the physics club in person without fail. But, it's just like there are workshops from like 2015 that I just didn't know about that are on YouTube, but that like I get to go back in time and attend. So things like that can be very helpful.
I think my first trip actually in 2 years is going to be the March meeting.
Okay.
That happens. And then I have another conference it was supposed to happen 2 years ago, and every year they postpone it for a year. So we'll see if it happens in May.
Yeah.
So those would be my first in-person talks, other than teaching, in quite a while. Actually, a little nervous about traveling after all this time.
Yeah, it's I'm on sort of a similar schedule. I took my first trips for family in the last couple of weeks, and it was it was a surprise after 2 years of not traveling. But let's see. So people are coming in. Hello, Leonid. We have at least one of the organizers of the Physics Club series here.
Hey.
How are you?
I'm good. Listening about your travel experience.
Yeah. So this semester it's you and Laura and David Poland.
Yeah.
Right? And David's here too. Hi, David.
Yeah. So actually, I wanted to thank Christian for being so responsible.
Oh yeah, it just worked out. It was kind of lucky that this is the day that I picked to keep things off of my schedule as much as possible, and this happened to be the day that we were having the talk. So, it worked out. Wouldn't have worked out well if it was on a Tuesday, I'll tell you that. But
fair enough. Do you want to go to full screen on your share, Chris?
oh, am I not on? What are you seeing?
Oh yeah, sorry. We're seeing what looks like Acrobat.
Oh, you're seeing my whole screen here?
Slide sorter.
Right, there's a sidebar with the feature.
Interesting. Okay, so I see. I'm sharing within a window is what's happening. I did not realize. Tell me if it still looks like that.
That is full screen. Yeah, that looks great.
Okay, I didn't change anything, by the way. I don't know why it's working now. That's
how it goes.
Participants can now see your application. Like, it's fine. I think if I've learned anything, it's to be much more flexible. So
yeah,
it'll be fine.
Yep. So what's the Bio-Inspired Institute?
It is new, or at least it's 2 years old. This is part of the reason why I moved. It is basically an institute at Syracuse that is cross-college engineering and physics, engineering and arts and sciences, including physics and chemistry and mechanical. The idea is to, be inspired by biology and use that to create and to figure out how to make new kinds of materials.
Okay.
Which, you'll kind of see some examples of that, I guess, or at least the inspiration part in the talk here. Just to kind of get the idea across, but it's still pretty new and it's still kind of being established. Obviously, things slowed down quite a bit in the last 2 years in terms of, we're still waiting to have our kickoff events. Actually.
Okay.
Oh.
Yeah, sure.
Maybe it's time to.
Yeah. Should we?
Yeah, like around 30 people. Yeah, so I think that you can forge ahead. Yeah.
Yeah. So let's see. Let me just check that I am on the. Yeah. So you can hear me okay? My microphone is all right. So welcome everyone to this week's Physics Club. My name's Jack Harris. I'm a professor in the Physics Department. For those of you who are joining us from outside the department, it's a real pleasure to have Christian Santangelo with us today. Christian and I overlapped very briefly in Santa Barbara, but I got to know his research on a visit to UMass Amherst a few years ago, and he's been on my short list to have come and give a physics club for some time. So Christian got his PhD from Santa Barbara in 2004, working with Phil Pincus. He was a postdoc at the University of Pennsylvania and then joined the faculty of UMass Amherst until March of 2020, when he joined the faculty at Syracuse. His group is a leader in theoretical understanding and modeling on the role of geometry and topology, and specifically in the phenomena of folding and the role that these concepts play in various materials and mechanical devices. And anyway, we're looking forward to your talk very much, and I will turn it over to you, Chris.
Great. Thank you very much for the introduction. I will do my best to speak up and make sure that my microphone is actually working, but obviously if something goes technically wrong, please just stop me. The other thing is, as you know, I know that there's a bit of a lag with Zoom, but I think that it's always a little bit more of a fun experience if people feel free to try to interrupt to ask questions rather than waiting until the very end. Especially if your question comes in somewhat early. I heard a rumor that there might be some first year physics students here. So this counts especially for you if you are indeed here. So what I am going to tell you about is some of the work that we have been doing in the group recently, trying to understand really what amounts to fairly simple seeming mechanical structures. Okay, so, but before getting to that, I thought it would be useful just to have one slide just on the kind of general problems that we actually work on. So I'm going to assume that you can see my mouse pointer, but tell me if you can't. But we've been doing a lot of work for a while in a very broad field that some people like to call extreme mechanics. But the extreme here doesn't refer to anything very extreme. It really just refers to the fact that the structures deform quite a bit. And so that's kind of, they're extreme deformations. And that brought us to thinking about problems of origami and the mechanics of origami. We've also done a lot of work, even a little further back, on what you might call self-folding structures. So these would be things that start out flat and have been patterned or designed in such a way that they fold up into various three-dimensional geometries. It's kind of a cross between general relativity and engineering, I guess. And then for a long time, I've been interested in the mechanics of various structured phases, especially liquid crystals. This image comes from a recent paper on, it's not really yarn, but on kind of twisted bundles of filaments. And of course, all of these things are somewhat related to each other in the sense that they all take advantage of using our understanding of geometry to make predictions about how these structures actually behave. And in fact, because I'm a theorist, I especially like doing this. One, I like geometry, it's fun. But on the other side, I think when the physics is dominated by geometry, you can often say things that are fairly universal, that don't necessarily even require hardcore simulations to understand. And so that's kind of the approach that we have been trying to take. Okay, so that's the broad overview. What I want to talk about today, the place that I want to start what I want to talk about today is something really simple. What happens when you actually deform a solid, okay? And and everybody knows, because presumably you've all deformed solids before, if you take a hunk of solid and you squeeze it, what happens is that, it deforms in such a way that perpendicular to the axis that you are squeezing it, it will actually grow, right? The material will actually flow outward. It's kind of like you're squeezing stuff and it's just kind of squirting out the side. And that's really how a lot of materials behave, especially a lot of materials that you can run into in nature, or sorry, not necessarily in nature, but a lot of human materials. That's all quantified by this thing called the Poisson Ratio. That's just the amount that the structure grows in the perpendicular direction divided by the amount that it shrunk in the longitudinal direction. And then people like to throw in a minus sign. So a typical material like the one that I'm showing here, that has a positive Poisson ratio. It's usually, as Jack pointed out, it's about 0.3, right? But obviously in real life, it can vary a little bit, but most materials have a positive Poisson ratio. And then there's this. Again, this is Zoom. I can't do my usual song and dance, but this is a tree, right? I don't know if anyone knows what this tree is. Maybe some of you can guess since I highlighted the Poisson ratio. Well, this is cork, okay? And cork is kind of a cool material. There is a really good reason why cork is what you use to stop up bottles. It turns out that when you squeeze cork, it does not expand in the perpendicular direction, or at least it doesn't do so very much. It's basically a material that has a very small, almost zero Poisson ratio. Okay, and so it's actually kind of, I don't want to say it's unique, but it's kind of a weird material in the sense that it doesn't seem to behave the way that our regular materials do. So why is that? Well, here's a picture of cork as seen through a microscope. This actually this comes from Robert Hooke of, I guess, inventing the microscope fame, right? So this is a really old picture, and you can see that when you look at cork close up, it's actually formed of these cells. It's got a cellular structure. I assume no one's surprised because it's actually a plant, right? Plants are made out of cells. But when you zoom in on those cellular structures a little more closely, there we go, you actually see that those cells are corrugated. And in particular, there's lots of empty space in between, okay? And so what happens when you take cork and you actually squeeze it is the cells themselves collapse, okay? And that's assisted in part by the way that the structure has these undulations in it. But basically, the important thing is that when you're squeezing it, instead of forcing the material to flow out in the perpendicular direction, it just collapses, right? And so that's where it acquires its zero Poisson ratio. So in fact, it's an example of something that people call a mechanical metamaterial. And once you start thinking about some of these weird biological materials and you look around, you'll notice that there's actually quite a large number of materials in biology that have various internal structures, and those internal structures give the materials the kind of behaviors that that they actually have. So there's carnivorous plants that change their shape because of the internal structure that the tissues actually have. Spider silk is it's supposed to be stronger than steel, essentially because of the way that the proteins are structured inside of the silk. Shark skin, I don't know if you do this, but sharks are basically armor plated. This is a zoom in of shark skin. It's made out of these, they're not actually teeth, but their name comes from the word for teeth. And this structure actually endows shark skin with the kind of anti-fouling, that's antibacterial properties that it has, and the way that shark skin allows the shark to actually glide through the water. All of that comes from the structure of these materials. And so obviously people have been working on trying to figure out ways to take these kinds of structured materials and make artificial structured materials. So this is where, this is where a lot of this field is going. They call them architected materials because I think, actually, I don't know why. I think that people just like to make words up. I'm pretty sure architected is not a word, but please correct me if I'm wrong. But these are materials which are often 3D printed, okay? Or in one case, which I'll point out just because I was an author on the paper, are folded from origami, but basically inherit a three-dimensional or a two-dimensional structure where there's lots of holes and there's struts, and because of this internal structure, these materials actually have a number of kind of fantastic properties, which I'll tell you a few of them in a second. But one of the interesting properties is that they're actually often reprogrammable. So the example of the origami is neat just simply because you can take the same structure and kind of futz with it in various ways and change the stiffness completely, or create regions of low stiffness embedded in high stiffness, basically anything you want. It's a completely, flexible programmable material, with the caveat that, of course, you have to make it out of something, essentially a sheet, okay, that you have to learn to fold. So, there's lots of people kind of thinking about these kinds of things, and we've also been working a little bit in this area. So some of the kind of fantastic properties, and actually the one that almost everyone talks about, is Oxetic Materials. So if you imagine something like this thing with the counter with these squares, where the squares are kind of connected at these hinges, you can convince yourself, and if not, at least I hope the sequence of pictures will convince you that, this sequence of squares could collapse essentially biaxially, the same in both directions. And because of that, actually, something like this has a negative Poisson ratio, which is extremely rare in nature, because essentially when you compress it in one direction, it compresses in the perpendicular direction. Here's an example from an origami fold pattern that has the same property. And I'm showing you these things in 2D because you can see them in 2D, but there are three-dimensional versions of all of this, just so that you know. The other thing that these things have, the other thing that these things have is that, you know, they don't necessarily have zero bulk modulus, but especially things like the origami sheet, the thinner it is, the easier it is to stretch and compress it. And so you can get the bulk modulus, the resistance to compression, to be essentially as small as you want. This thing on the right, this is going to answer the question that's in the chat, by the way. This thing on the right is a material that I don't have the scale bar here. This is microns. About, I'll have to double check, but about if you see the mouse pointer going left and right, that's like 100 microns, I think. But that's an estimate. I'm sorry, I don't know what happened to the scale bar. But this is a material whose shear modulus is very small, depends on essentially the properties of the hinges between these structures. It's a, you know, it was some crazy 2-photon photolithography thing that they managed to make, Martin Wegener's group managed to make. And yeah, so like I said, it's got a very small shear modulus. And I think that's about the smallest that people have managed to go. It's pretty small. And obviously there's nothing wrong. There's nothing that would prevent us from scaling this up to be a material with 100 micron structure that is sort of human scale, but I am not aware of anyone that's actually made such a thing. Probably because the 3D printer involved would be kind of large. Okay, so so this is how you know, these are all examples of mechanical metamaterials. So here's where I come in. A lot of what I just showed you is engineering, in the sense that these are people trying to design structures that have particular properties, and we want to be able to do this too. Okay, but in order to do this, you know, I'm like the curmudgeon, right? Like I'm the guy, I have to take bio out of bio inspired, right? By like taking these things and making real materials, right? I want to take the you know, computation part out of computational design, right? I want to understand how these materials get their properties so well that, you know, any Yahoo could come in and just design them by hand, and you don't need to use a computer. A lot of these other kind of intricate materials are not necessarily designed by people, but are designed by, you know, some computer program, some algorithm that somebody wrote. Okay, so so it sort of helps to think about where a material would get its properties from. And so I want to step back. I want to take something much, much simpler seeming. This is a random spring network that you're looking at. Okay. And so I want you to imagine that there's a network of vertices, there's a bunch of springs connecting them. And to imagine putting an elastic energy that just penalizes changes in the spring's length. Okay. So it would look something like this. You would take the actual length of each spring, you would subtract some equilibrium length that could vary from spring to spring, and square it, right? And then obviously there'd have to be a spring constant. And so the idea is that with a model, microscopic model like this, if you take this spring network and you deform it in some way, then you'll get different changes in the spring length, and those are going to determine the mechanical properties of the material. And that's kind of the standard story of how you might go about trying to predict the properties of some of these things. But here's another example of a different spring network. Okay, same energy. And what I want to show you with the spring network, so I want you to imagine that this is periodic boundary conditions. So if you look at the vertices here, they perfectly match up with some of the vertices down below, and the same on the right and left side. But I'm not going to show you all the periodic images anymore, because they're actually kind of a pain to draw, honestly, and they kind of get in the way. So so now you imagine that you take this thing in periodic boundary conditions and you compress it. Okay, and so when you do that, what you can find is that a network like this can rearrange itself in such a way that none of the springs change their length. Okay, and so if you had something created out of a spring network like this, it would actually be a material that didn't cost you any energy to distort, to deform. Okay, I mean, in practice, the actual deformation would depend on the angles here, but you can imagine that if you make the connection between the springs thinner and thinner, you can essentially take the elastic energy cost of deforming down to zero. Okay, so let's try to understand why this is, and then I'm going to show you afterwards, from this somewhat pedestrian sounding problem, some things that I actually think are really cool. Okay, so no, so just to answer the question from on the chat, the angles can't remain the same, it turns out. The lengths can remain the same, the angles have to change. So if you had a little bit of elasticity, torsional elasticity in the angle, that would be the scale, that torsional elastic constant would be the modulus that sets the actual elastic properties of the material like that. But it wouldn't be the spring modulus, which is the point. Okay, so constraint counting, right? So how do you actually understand if something like this is rigid or not? We're going to take a page from Maxwell, okay? And imagine that we have a spring network, and that spring network has V vertices and E springs or E edges, okay? And so what we want to do is we want to look at all of the vertices, and we'll try to count how many degrees of freedom are embedded in all the vertices. So there are, obviously in D dimensions, there's VD degrees of freedom. There are E constraints. There's one length constraint for every edge. And so if you wanted to count how many different ways there are to isometrically deform this, without actually stretching the edges, it seems pretty easy to do. You just take the number of degrees of freedom and subtract the number of constraints, and there you have it, okay? By the way, these isometric motions, they're often called zero modes, and I'm almost definitely gonna slip into calling them that, so we might as well just start now. So here's an example. Here's a simple network, and I've taken away the little curly parts of the spring. Okay, and so this network has 4 vertices in 2 dimensions. That's 8 degrees of freedom minus 5 edges. And so you find out that there should be 3 zero modes. And that makes sense because this is rigid. There's no way to deform this without stretching the edges, except for the 1 rotation and the 2 translations that you get in 2 dimensions. And then you have this network. Okay, and this, I've added 1 extra red bar. Okay, and so we could do the same counting, right? We could just take the vertices, it's still 4. We can subtract the number of edges and we get 6. And so it should have 2 zero modes, right? And okay, obviously that's wrong, right? Because it's rigid, so it can still translate in 2 directions and rotate once. And so obviously this simple formula, there's a mistake in it. And where the mistake comes from is that there's actually a redundancy. That extra red edge, it doesn't do anything, right? It was already rigid before. I can add 100 edges to it if I want, right? In whatever shapes I want. If it's rigid, right? And so one of the really cool results in this field, I think it's cool, is that if you wanted to think about the redundancies, the dependencies between all of the different constraints, one way to identify them is to look for something called self-stresses. So self-stress is just an assignment of tensions and compressions, basically extensions and compressions on each of the bonds, such that the force on all the vertices is balanced, is 0, okay? So this particular structure with the extra red beam, that has at 1 self-stress, and so one of these constraints is redundant with the other ones. Okay, and so because of that, you have to add a correction for the redundancy, which essentially amounts to counting the self-stresses. So there's this now famous formula that tells you how to count the number of degrees of freedom that a structure has. But now you know that you have to calculate the number of self-stresses as well, and that will tell you essentially whether or not there are enough constraints to keep your system rigid.
Chris, just to interrupt, can you explain this diagram on the right? Is it easy to see how to spot something as a self-stress?
It's certainly easy when you get the hang of it. I mean, you can see it. Maybe it's easier to see that there's no self-stress on the one on the left. Essentially because you couldn't balance the force on these two corners, right? Because of the fact that, you know, you could put an extension here and an extension there, and then there would be just adding vectors together, there's an unbalanced force.
Okay.
So yeah, I often find it's easier that way, intuitively. Okay, so here's an example of a network, and this is the same kind of network I showed you before, but now I'm going to point out that each vertex has 3 edges, okay? And so now we can do the standard counting. And in the standard counting, it turns out that, yeah, look, if there are V vertices, I have V times D degrees of freedom. There are 3V/2 edges, right? There's 3 edges for every vertex, but each edge connects 2 vertices, so you have to divide by 2 to get rid of overcounting. And then you'll have to take my word for it that there's no redundancies in any of these constraints, okay? Which is, again, it's not super obvious to see, if you ask me. And I'll show you in a second, it's really not super obvious to see.
You're talking about a flat system, right? Or
I'm sorry? Say that again.
It is not 3D, it's flat.
It's 2D. Yeah, it's flat. Yeah.
Okay. Yeah, because in 3D you can definitely. Okay.
Yeah, in 3D, exactly. In 3D, you would count differently. I'm going to show you all, to be honest with you, mostly things in 2D, and mostly because it's easy to see on a slide, for the record. Okay.
Could I ask a question?
Yeah. Yeah.
So I imagine, like, if you add 2 self-stresses together, you get a third valid self-stress. So is this more like counting the dimension of the space of self-stresses?
Yes, that's correct.
Okay.
Okay. Yeah, thank you for that. I probably should have said that. Okay. So in any case, this is the counting for this system. And so if there's no redundancies, there's no self-stresses here. And so we can count how many 0 modes this is supposed to have. It turns out it's V/2. So it's extensive in the number of vertices. The more vertices you have, the floppier this thing is supposed to be. So let's test it, right? So if you take this system and you stick it in on a computer, okay, and imagine compressing it, or actually instead of compressing it, what I actually want to do is just change the equilibrium length of the springs and keep the size of the box the same. That's essentially equivalent to changing the size of the box and keeping the equilibrium length the same. And so, and then what I'm going to do to measure the rigidity is let's just ask whether it has a shear modulus, okay? And so for large equilibrium lengths, it's not too hard to compute. There is actually no shear modulus. And then you reach this funny point here. And by that point, by the time you reach this point, the spring network has changed what it looks like. It actually looks more like what I'm showing you here. And I don't know if you agree with me or not, but I still can't see any obvious places where I would put in a self-stress, okay? But at that precise point, it turns out that the system does develop a shear modulus. And so it basically rigidifies, okay? I haven't changed the number of bonds. I haven't changed the way that we count anything, okay? It's just I reach a special point and the system becomes rigid, okay? So, you know, we want to understand what's going on, okay? And we wanted to understand what was going on with this. And so I'll tell you a little bit about that, and then I'll tell you some of the cool things that leads to, okay? And by the way, there's a comment that this feels like homology, and that's probably not an accident, but I don't know to what extent people have really exploited that before. Okay, and so if you do the analysis on this spring network, you can show that right at this point where it switches from being floppy to elastic, suddenly the system develops one self-stress. So somewhere in this, there's some way of assigning tensions and extensions that are super not obvious, and but there's one way to do it. meaning that there's one redundancy in the system, okay? And it also, though, unfortunately develops one extra zero mode as well, okay? So even though there's a redundancy, it appears to be one bit floppier, I guess, one dimension floppier than it used to be. And so presumably it's compensated. So why is it that it's actually rigid? And so I did it, yeah.
Quick question before. You are saying that
Leonid, you've muted yourself.
Yeah.
Can you unmute?
yeah, sorry. So this L bar 0.6 is special or whatever. I mean, in which units? I'm not sure I understand.
Oh, sorry, I didn't tell you what the units were, I guess. The units are that L is actually 1. Capital L is 1. So it's at, so this is, let me put it back. It's about 0.63. There's nothing special about it, by the way. If I draw a different spring network, it'll happen in a slightly different place.
Okay, so L bar is what, kind of an average length of a link, or what is it?
It is the equilibrium length of all of the links. We're just set them all to the same number.
Equilibrium length of the sum of the lengths.
Nope, each individual link has some equilibrium length L bar. And whether or not it can achieve it is a different question, right?
It's 0.6 of the entire size of the system.
Yeah, that doesn't make sense, does it?
No.
It doesn't make sense.
Yeah, that's why I'm asking.
Yeah, you're right. And you know what? I cannot remember. I'm so sorry. I can't remember what the units are.
But at least, can you tell in terms of, intensive or extensive quantities? So your system kind of, I understand it's not periodic, but can you make it larger and larger and everything is the same, or things are changing?
It is periodic, and you can scale everything up, obviously. And oh yeah, you mean if I just look at a bigger system? That comes out the same. And I just can't remember
without changing the size of the individual spring.
Without changing this, yes. I think if I understand your question, the answer is yes. So if
the question is what is L bar? I mean, then L bar is completely enigmatic to me, but we can discuss later. Yeah,
okay. So the answer, unfortunately, what I'm going to tell you, the answer is clearly is that L bar is arbitrary units, and obviously what we did was we started the simulation at L bar 1, and then we shrunk it down. But we can definitely talk about the details later. The point is that there is an L bar where this happens. Okay. So let me go through the. Okay. So I'm going to give you an even simpler system where we can understand exactly what's going on. Okay. So here is a version where we have basically N springs that are. It's basically a polymer, right? It's N springs that are pinned down at both ends, okay? And so we could think of, just to be even more concrete about how to think about this model, we can imagine that we take the position in 2 dimensions for each of these vertices, and we just concatenate them into a very large vector. And then the constraints that we want to have, okay, is that all of the springs should have the same equilibrium length. So if they are able to achieve that length, that means that, when you take the distance between any pair of adjacent vertices, you're going to get L bar squared. Okay. And so that's what this equation here is representing. Okay. This picture, by the way, this picture has springs that have lots of different lengths, but at least for now, imagine that we're looking for something where everything has the same length. Okay, and so, yeah, okay. And just for technical reasons, I'm going to use the length squared here, but that part's not important, but just remember that when you see these 2's floating around. Okay, so now let's say we want to understand what's going on in the mechanics of just this 2-dimensional chain. One of the things you could do is that you could start from a configuration and you can look at a small deformation. Okay, so we can expand everything to linear order. And when we do that, we'll get a matrix. which goes by lots of different names depending on who you are. You can call it a Jacobian or a compatibility matrix or rigidity matrix. But it tells you how the lengths change when the vertices are displaced. Okay. And if you look at this matrix, right, you can convince yourself that if there are n vertices, it has 2 n columns and n+1 rows. There's a row for every edge, and there is a column for every degree of freedom in this vector U representing where the vertices are. Okay, and then the zero modes are the things that live in the how should I put this? Well, I'm going to say this and then I'll say it in a different way. The zero modes are the things that live in the right null space of this matrix, and the self-stresses are things that turn out to live in the left null space of this matrix. And so what this means at the end of the day is that you can count the number of degrees of freedom simply by taking the number of columns, subtracting the number of rows, and that is going to equal the difference between the number of zero modes and the number of self-stresses. And that turns out to be a linear algebra thing, not necessarily even a physics thing. It's just the way that matrices work. Okay, so let's look at this system. Let's take this, right. If the number of self-stresses is 0, and it's definitely 0 in this case, then it's not hard to see that the number of zero modes is n-1, if n is the number of vertices. That's just linear algebra. Okay, so now let's look at what happens when we take the system and we pull it out so that it's straight. Okay, so now things are a little different, and it turns out there is a self-stress. I'm showing you what the self-stress looks like. You could just put a constant extension on every bond. Since these vertices at the edges are pinned, they don't move, right? And so there's one self-stress, and that means that the number of zero modes has to be n. It's 1 bigger than it was before, which is exactly what we saw in the other two-dimensional system. Okay, and so it seems as if this system should in fact be a little bit floppier than it was before. Okay, but when you actually look at what the zero modes look like, you can convince yourself that there's something missing, right? So this is what the zero modes do. They all look like vertical displacements of these vertices up and down, okay? Because when you look at the length of these springs as these vertices are displaced up and down by some amount delta U, right? The Pythagorean theorem tells you that the change in length scales like delta U squared, right? And so, the problem that we have in doing the analysis here is that we've been doing everything to linear order, and there are obviously deformations that you have to go at least one order higher, if not even higher, in order to understand what is actually going on in the system, okay? So if you expand the lengths to second order instead, okay, then I'm just going to tell you this, that you can show that that you can find a solution to this equation so long as you deform along a zero mode, okay, and the zero mode satisfies some extra quadratic constraint, and this extra quadratic constraint depends on the self-stress. Okay, this is a bit of a look, it's a formula, right? We can derive it. And it's telling you something about what it takes to actually deform the structure in a way that doesn't change the lengths of the springs, but to second order in the displacements. Okay. So now you can ask, well, is this satisfied by the system? And it turns out that actually it's not. You can show, and it's not too hard to show because all of the self-stresses have the same sign, that this thing is actually always positive definite, or it's always negative definite, but it's never equal to 0. And so in this system, right, it tells you that this thing is rigid. Now, it's obvious that this thing is rigid when it's a single chain. It's much less obvious that the structure to the right has the same property. That is that when you analyze the actual self-stress, it turns out that this construction is always positive definite, and that tells you that, in fact, there's always this second order, that it's always rigid at least to one higher order. And that's actually why it rigidifies. We have seen the same thing in all kinds of mechanical systems. So here's an example from Origami, which is one of my other fun physics projects, trying to understand how things fold. And if if you imagine that, this is a sheet of paper and you fold it along these 4 folds and there's this vertex in the middle, if you replace all of these folds with edges and you replace the boundary with edges, then you'll get a mechanism just like we had before with the springs, except now this is the mechanism in 3 dimensions that represents the folding of this piece of paper. And it's not too hard to see that there's actually a self-stress here. So when we're actually analyzing the mechanics of an origami structure, you get something kind of interesting. So you do get a quadratic constraint, or actually a whole system of quadratic constraints. And you can solve those, but when you solve them, when you look at the actual configuration space of a folded structure, what you see is that there's 2 ways to fold this. Okay, I've drawn pictures of what the 2 ways look like. But what I'm doing here is I'm plotting the folding pathways as a function of 3 of the angles. Okay, it would be great if I could show it to you with 4 angles, but as it turns out, we don't live in 4 dimensions. So I'm showing you a 3-dimensional diagram, projected on a flat slide. Okay, but you can clearly see that there's a point here where there's this crossing, and the whole thing is 1-dimensional, has 1 degree of freedom. But if you were living at this point where these things cross, it's easy to see how you could get a little bit confused. Here's another example of a simple mechanism. This is usually called a 4-bar linkage that is designed so that it has these 3 points where you have self-stresses, and those self-stresses tell you that you have these crossings that appear. Okay. And then there's a whole family of theorems that tell you the properties of these crossings that you can have. So it turns out that you can only get these, if you choose lengths such that you have a system that has some of these critical points, you can deform the lengths just a little bit and you end up with smooth configuration spaces. So I'm showing you one example here where, if you set the length of all 3 bars to be the same, to be equal to A, which is the distance between these 2 pinned vertices, then there are 3 critical points. There are 3 branch points, let's say, where the configuration space basically has different pathways that you can follow. If you make this L2 bar a little bit longer, then you end up stuck along the red curve. Okay, this is periodic boundary conditions. What I'm showing you is I'm plotting these 2 angles, theta 1 and theta 2. If you make the L2 a little bit shorter, then you end up in following these blue curves. Okay, and if you look at the red curves and the blue curves, it turns out there's 1 red curve, okay, and there's 2 blue curves with periodic boundary conditions. That is the red curve, it has a 1-component configuration space. The blue curve has a 2-component configuration space. So in fact, the topology of the configuration space itself for the structure changes when you change the length of the bars, okay? And so what we've been trying to do is take advantage of that to figure out how to actually design mechanisms that have certain properties. So that's kind of the second part, or the last part.
I had a question about the previous slide.
This one.
What are the arrows on those black lines?
Yeah, I'm not going to tell you here. it's a little bit complicated.
Okay.
But if you want to ask me, send me an email. I'll tell you by email.
Great, thank you.
Okay. So, so you can show that you can take a system like this. You can choose the lengths of the bars in such a way that you end up with some number of critical points. Okay, and then you can deform it away from that, and you have a lot of control over the topology of the configuration space. Okay, so here's a bunch of different ways of breaking up the configuration space. Here's one that's going to come up in a second. This one has it winds around in both theta 1 and theta 2. And here's all the things you can do where you keep 1 of the branch points. Here's all the things you can do where you keep 2 branch points. So basically you can generate all kinds of different topologies. And the only thing that's necessary is to actually identify where we are to identify a place where we have one of these critical points where you have this extra self-stress and you have this extra quadratic constraint. It should remind you a little, I don't know if people know this, but there's this really neat theorem from this guy Kempe from way back in 1876 that has been popularly summarized as you can create a linkage to sign your name, okay? And in other words, you can basically get a linkage where one vertex traces out any curve you want. So here's a cool example that I found on Wikipedia, okay, where it's tracing this curve as some special name. You know, it doesn't really matter what it's called, but it's a particularly simple linkage, right? It's really only two bars and one pinned vertex, and this outer curve traces this thing out. There's a little bit more, I guess there's a little more going on there. So here's an example of an ellipse. And so now you can ask, okay, great. It turns out that I can make a linkage to trace out any curve I want. What would it take to make something simple like an ellipse? I mean, surely that won't be very complicated, right? Ellipses aren't that complicated. And this is what the linkage looks like. It's kind of cool, right? But you can sort of get maybe the idea that it's possible to generate a linkage that will have a vertex that traces any curve, but maybe the linkage isn't going to be so simple to do it. But we're kind of talking about something different. We don't care so much that it traces out an ellipse per se. What we're just interested in is just kind of ensuring that we've generated a linkage where the configuration space has the correct number of components or is connected up in the way that we want. So the first thing we need to do is figure out how to identify where these critical points actually are. And can we do it? And the answer is yes. Okay, we have there's a mathematical object we generated, an antisymmetric tensor, which is 0 anywhere that you have a critical point. And so, you know, we can prove this. And by the way, this is what the arrows have to do with. So I can, like, you know, for the person who asked the question, it has to do with this object. But so this gives us a way of actually identifying critical points in mechanisms with a particular connectivity. And then from here, right, once we find such a thing, you can imagine taking that structure and perturbing it a little bit. And at every critical point, you're going to break it up, and it'll break up into a pair of hyperbolas, I guess, in English. And it'll either look like this, or if you deform it a different way, it might look like this. And you can control how that happens in order to actually generate the topology of the configuration space that you want. Okay, and then of course, you know, it's all you know, fame and glory, I guess. So I'll show you two things before I finish up. We're actually kind of on time. So I showed you this example of this linkage with the 3 bars. And so now what I'm going to show you, so there's is the 0, all the places, all the values you can assign L1, L2, and L3 to in units of A, such that you have a critical point. And this is what it looks like. This is the surface. If you pick L1, L2, and L3 anywhere on this surface, then there's one critical point. And you'll see, though, that there's places where these surfaces intersect. There's actually 2 sheaves that come in this way, and they intersect along this black line. And it turns out if you pick a point anywhere on the black line, right, where you have 2 intersections, where we have 1 intersection between 2 surfaces, then you have 2 critical points. And then there's this special point right here where all the lengths are the same. And there you have 3 surfaces intersecting, and that gives you 3 critical points. The volumes that are defined by this surface, and the surface is just the surface that's generated by looking for the zeros of that object I sort of you know, skimmed over. The different volumes of this correspond to different topological classes of configuration spaces, right? Different ways of breaking up the critical points. So all we really need to do is figure out how to pick, you know, choose the volume that we want to live in, pick a set of lengths that live in that volume, and the structure will move, you know, at least in its gross features in the way that we want. Okay. By the way, this is the side view, and I'm really just kind of pointing out that somebody can ask me about this, I can relate this, even though this is a much simpler system. You can, it's kind of interesting to point out that there are points that are inaccessible. These are points that are actually stressed. And it turns out that this configuration that I showed you, the one that has the self-stress, this is something that lives right at the edge of a space like this. Of course, it's much more complicated in this case because this has many, many edges. And so this would be a surface in, just countlessly many edges, right? And so it's very hard to plot that. This is the version where you only have 3 edges, but the geometry of this should be roughly analogous, that there's always a critical point between the region where you can't actually access because you actually have to stretch the springs, and regions on the inside where you can and you have branch points. So what can we do? So I'm going to show you one example of something we can do. So this is an example of a very, a linkage that we didn't invent. This is often called the Kane-Lubensky chain. And the important part about this is that it supports a soliton. So I'll just show you what the soliton looks like. Okay, there it is. It just travels from one end to the other. And it has to do with the fact that this linkage here, this blue line, black line, and blue line here, that's one of those 4-bar linkages, but it's the one, it's chosen in such a way that this curve winds around, that the actual configurations, theta1 and theta2, both wind around by 2 pi as you move along the 1 degree of freedom configuration space. And so when you chain a bunch of these together, you end up with a soliton that moves. And so what we've been playing around with is whether we can create a kind of gating mechanism, something that's actually robust because it relies on the topology of the configuration space itself. So here's an example where you can take one of these Kane-Lubensky chains and attach 2 bars and 1 pinned vertex. So this vertex is fixed, okay? But you can measure its distance to the vertex above. We'll call that D. You can go through this procedure and identify all of the ways of choosing, say, D and L2, this length D and that length L2, in such a way that you end up with a critical point. Okay, this is what that space looks like. Okay, we picked some points arbitrarily. So if you set L2 to 4A and you set D to 5A, then you actually have a configuration space that should have some branch points in it. And then if you increase or decrease D by some amount, you'll end up with 2 different, if you increase it, you'll end up with 1 topology. If you decrease it, you should end up with a different topology of configuration space. And I put phases in quotes here because this has nothing to do with phases in any traditional sense, but we got to call them something. So this is a bit of a complicated thing to unpack, but this is the configuration space. So we're calling this vertex 1, this vertex 2, that vertex 3. If you look at the black lines, that is the configurations that you get. We're just plotting the 3 rotor angles, the 3 angles of this bar, and this bar around this pinned vertex. And if you choose D to be exactly 5A, you get a critical point. You actually get 2 critical points, 1 here and 1 there, okay? And in fact, when you perturb D, when you decrease the length of D, you end up following the red curve. And when you follow the red curve, you can see that theta1 and theta2, they wind around completely. They have the same winding number that the Kane-Lubensky chain had. When you increase the length of D, however, when the trajectory reaches this critical point, this branch point, it actually turns around. You've broken the critical point the other way. So now you have hyperbolas facing in the other direction. And so there's this gap that opens up. And so ultimately this rotor that I'm pointing at, number 2, it can't get all the way around anymore. And so you can guess what happens, right? You have the case where it's open, right? And the soliton just proceeds just like before. And then you move I just want to point out how similar, I did this on purpose. These are almost in the same place, okay? And in the other case, you end up with a completely gated signal. You cannot send the soliton through at all, okay? And even if you fabricated this thing, even if you didn't get it exactly right, the fact that this depends on the topology of the configuration space means that it should be completely robust to, basically fabrication errors. So I won't dwell on this, but we've made some with Legos. Okay, Legos are turn out actually to be a pretty cool research tool. So what do we want to do? Well, one of the obvious things and something that people are really thinking about is actually creating real programmable matter, right? So if you can design structures that have some of these properties that we can take advantage of these critical points, we should be able to create materials that can essentially sense their environment. Maybe a few of the bars will grow or shrink or, and then change their physical properties depending on what's actually happening. And the flip side of this, that actually there's a number of people thinking about this now in different kinds of systems, is what you might call mechanical computing devices, or materials you can count on. If you want, basically materials that can process information in order to decide what properties they're supposed to have. So that's all in the far future, presumably, but hopefully this is a step along the way to doing that. So with that, I just, obviously this is the obligatory slide that tells you that actually there were a whole bunch of people that have worked on various parts of this research. The research I told you about from my group is primarily the work of a former postdoc, Brian Chen, and two students, Mary Elizabeth Jimbo Lee and Michelle Berry. I've had a number of collaborators on various parts of this project, but have been working, a lot of that Lego stuff was actually done by this guy, David Limberg, and the stuff on the Spring Networks was part of a collaboration with Lisa Manning, who's also at Syracuse. So with that, thank you for your attention. I think I finished mostly on time. And if there are any questions left over, I'm happy to take more.
Okay, let's all thank Chris for the talk. There was definitely some chat in the chat.
Yeah, I tried to answer a lot of that. I'm not gonna delve into the catastrophe theory stuff. I'm curious to see, curious to understand it a little better. I don't have any comments or anything useful to say about it right now.
So let's prioritize people who raised their hand. Leonid, do you want to go first?
You know what? So chat was mentioned. Now when I open the chat, actually, it looks like this question was kind of asked about catastrophe theory. So, but maybe one step aside. So essentially, as far as I understand, one can imagine writing a potential energy and account for the constraints, and then you'll have some function. If it's elastic springs, it's kind of probably some kind of a polynomial. Mm-hmm. And then the question is that it's polynomial of a certain number of variables, and then you may ask, what are the minima of this polynomial? And that's basically what the bifurcations of catastrophe theory is about.
Right.
So I just wonder if this kind of analysis, just at the basis of the minimization of some energy functional was done, and whether you can classify basically the networks or the arrangements of the links using some mathematical structure and some group theory.
That's a good question. I don't know about the group theory. My sense is that probably not. It hasn't been looked at in the way that you're thinking. One thing to kind of point out is that using an energy functional isn't totally useful. It turns out and I didn't really dwell on this because it's kind of technical, but the object I showed you before that I said is 0 when you have a critical point, it has some advantages over doing an energy. The problem with an energy is you're looking for places where the energy is 0, but the energy is always positive, right? And so it turns out that that's sometimes a pain for a machine defined. the advantage of the object that I told you about is that the components change sign whenever you cross the critical surface. So it
Right.
tends to be a little bit easier to find that way. And I do think that there's a structure there, and I hope that, you know, we'll uncover a little bit more about how it works. But I don't think I know yet in a satisfying way what exactly that should look like.
Thanks.
John, do you want to go next?
Well, I guess a couple of things. But back to Leonid's first question. I mean, we can tessellate the plane with polygons. Okay, so you
Right.
gave us an example where each node had it was surrounded by 3 links.
Yeah.
You had a big length scale L, then you had this L bar that he was focused on, and then you had a transition at some value. So first of all, presumably big L is much larger than the average size of a cell. How sensitive then is this transition to the way in which I tessellate the plane? So that's the first question. Second question is, if I just think about origami, which I've never done, you know, I mean, I have a sheet of paper, right, and I can deform it. But if I bend it first, of course, then where it's going to deform is determined. So the question really that it's important is the nature of stability. I think that's why catastrophe theory probably comes up. If I really want to model this, I can use the Foppel-von Karman equations. So there's a 4th order system, but when I actually do the origami, there's time dependence. So my question is whether your constraint of this positive metric that you showed us very quickly is consistent with the maximum principle for, you know, the time dependence in the Foppel-von Karman equation. So those are the 2 questions.
Okay. I will tell you 2 things then. I will answer both questions, I think. So in the first question, if I remember, it was about how it depends on the precise nature of the tessellation, and it does only a little. And I, you know, if you think about, so the way that we generated the random 3 connected, the 3 coordinated network is obviously we just laid down a bunch of points and looked for a Voronoi tessellation. And, you know, it's true that the L bar, the critical L bar changes a little bit depending on what the realization you're looking at is. It doesn't change so much, but it does, it's always around 0.55 to 0.65 roughly. I just don't know that it means anything, or at least I don't know what that number means. A honeycomb lattice, or, you know, basically also has a transition around that number as well. Though I actually can't remember what the number is right now for the honeycomb lattice. I did actually check it. The second question, I will tell you, is that you can, with a little bit of effort, I didn't talk about this, but we have a paper where we can derive what I would call a kind of discrete equivalent to the Foppel-von Karman equation for origami, for triangulated origami, for actual triangulated structures. And so I think the answer must be that it's very similar already to what you're talking about with the Foppel-von Karman equation.
Okay, thanks.
Nick?
Hi, so to expand a little bit on the catastrophe theory remark, so catastrophe theory is basically, starting point is you have some classical potential function, and you look at the minima, let's say in particular stable stationary points, and vary parameters, and then at some parameter values, the number of stable solutions changes or they merge or something like that. That's the singularity. So, and it seemed like when you were talking about the branch, what you call branch points, the number of connected components of your minimum energy states was changing. So, so it sounds very much like catastrophe theory, although catastrophe theory normally is probably concerned with rather small numbers of degrees of freedom. And of course, you have rather a large number, and you probably have, or you seem to have, degenerate minima.
Right.
But at least sort of local structure of these places where the number of solutions undergoes a bifurcation might be described by catastrophe theory.
I think that's a good suggestion. It's definitely something to that probably is a good idea to look into, actually.
Get Gilmore's book.
Yeah.
Get Gilmore's book. Jack Harris knows all about it.
Yeah, Gilmore, Catastrophe Theory for Scientists and Engineers. I'm looking at it.
Oh, okay.
Very,
I've looked at some literature by Arnold, right? But it's very, it's very mathematical.
Arnold summarizes it very quickly, and Gilmore sort of lays it out.
Right, but Arnold also has very nice classification of bifurcation points, and I think that he found the relation to Lie groups here. I don't remember. I studied it when I was in college.
Well, Arnold and Tom did the original work, but the point is Gilmore is an exposition of the whole thing, which is much more readable.
Yeah.
Okay.
Yeah, no, that's good. That's good. I like this. This is why you give talks, right? Is to actually get good you know, good
Yeah, the talk was very interesting for me. Thanks.
Thank you.
If I can ask one question before we wrap it up, and maybe put in one more plug for a book, which is called How Round Is Your Circle?
Yeah.
There's this study of linkages, which of course was huge in the 19th century when you needed to transfer steam power, which is very linear, to all different kinds of motion. And this was elaborated very wonderfully. So I wanted to ask you about that 1876 result from Kempe. Did I understand you correctly to say that for like any arbitrary, presumably smooth closed loop, there is a linkage? And
Yeah.
is there a tractable recipe? Like if I give you some complicated analytic curve, how tractable is it to then generate the linkage?
The linkages themselves are super impractical, I'll tell you that. But the way that the proof works is that he actually generates a subset of sort of special linkages which perform certain kinds of arithmetic operations. So as long as your curve is an algebraic curve, so basically something you can generate with polynomials, then I think there is a prescription that will tell you how to do that.
Okay.
There were some complications in the original proof. Technically, the original proof isn't quite right because of all the branch points. And somebody had to come along later and kind of improve the design in order to get that. But yeah, this is exactly, their problem was, the whole point of that problem was just to figure out, they were really interested in whether they could take a circular motion and turn it into a true linear motion. So that's why he wrote that paper, and it, that problem was eventually solved, at least, as you can imagine.
Okay. All right, well, given the time, I think this would be a great point to pause and thank Chris very much. Chris's contact information is available on the World Wide Web if you'd like to continue these conversations, and he's graciously offered to be contacted. So thank you, Chris.
Yes, thank you for the invitation, and it was a pleasure to be here, I guess.
Yeah. Look forward to real life meetings.
Yeah. All right. Bye.
Bye.
Thank you.
Yes, thank you. Let me figure out how to get out of here.